Hello, today we're going to review how to graph rational functions. All of our rational functions are going to be rational, meaning they are a ratio of two polynomials. So we've got a numerator divided by a denominator. The first thing we want to do is to factor both the numerator and denominator. So in this case, let's start with number 13. We factor our numerator to be x minus 2 times x plus 1. Our denominator, we can first factor out a common factor of negative 3. So we're left with x squared minus 5x plus 6. And don't forget to factor out the negative from your second and third terms in there as well, because otherwise your factors will not work out correctly. So then we still have that negative 3 on the outside, and we can factor that quadratic to x minus 2 times x minus 3. This is the order that I like to go through the different characteristics of the function when I'm graphing it. Most of the order does not matter, but it's important that we are finding any removable discontinuities first. So for example, here we notice that we could factor out an x minus 2 from both the numerator and the denominator. So what we can do with that is set that equal to 0 and solve. We know that we will have a removable discontinuity, which will look like a hole on the graph, just that single point where the function is undefined, and the rest of the function is going to behave like this. So at x equals 2, we'll have that removable discontinuity, and we need to figure out what the y-coordinate is going to be for that. So in order to find the y-coordinate, do what you would do on any other function. Substitute a 2 into the function to find the y-coordinate. So our numerator is going to be 3, our denominator is going to be 3, so we will have a removable discontinuity at the point 2, 1. So we go on the graph, find the point 2, 1, and put an open circle to represent the hole that is the removable discontinuity. Next up, we want to look for the vertical asymptotes for the graph. To find the vertical asymptotes, well, this one only is going to have 1 because we are going to set our denominator equal to 0. Now, using the zero product property, we would have that negative 3 is equal to 0 or x minus 3 equals 0, but negative 3 is never going to be equal to 0, so it's just x minus 3 is equal to 0. So we will have a vertical asymptote for this function at x equals 3. So we draw that on the graph. I like doing this piece by piece just to break it down into smaller chunks. Then we can have our completed graph at the end. To look at the horizontal or oblique asymptote for these graphs, all of them are going to only have 1. Let's compare our leading exponent in both the numerator and denominator. Our 3 options is that our greatest exponent's in the numerator, in which case there would be an oblique asymptote for the function. Our exponents could be equal, like they are here, where we will have a horizontal asymptote. We will take a look at where in a minute. And if our greatest exponent is in the denominator, then the function is going to have a horizontal asymptote at y equals 0. So here, since they have an equal exponent as our greatest exponent in our numerator and denominator, there is going to be a horizontal asymptote at y equals a ratio of the coefficients. So we have 1x squared divided by negative 3x squared. So it's going to be at y equals negative 1/3. So we can go ahead and graph that, approximate where 1/3 is. Mine's a little too low over there. That looks better. Not straight, but this is why we are sketching and not doing an 100% accurate graph. Now, for our zeros, we are going to set y equal to 0, just like with any other function. But in this case, we would multiply both sides by the denominator, and we would just end up with the numerator equal to 0. So for finding any zeros, set your numerator equal to 0. So we have x plus 1 is equal to 0. So we have a 0 at x equals negative 1. So we go ahead and graph that point. If it helps out, write out your zeros and your y-intercepts as an ordered pair. For our y-intercept, all we're going to do is substitute 0 in for x, just like with any y-intercept of another function. And for these, this is one of the easiest parts because all of those terms are going to be 0. So f of 0 is just going to be negative 2 divided by negative 18. So it's 1/9. So we graph that point of 1/9. And then we know what's going on between these asymptotes over on this left side of the graph. The function is going to be close to the asymptote, hit this 0 and this y-intercept. Then it's going to curve towards where this point would be for the removable discontinuity, and then close to the other asymptote. We still need to figure out what's going on with the function on this part of the graph. So let's take any value that is greater than 3. Let's find f of 5. So we substitute 5 into the function. 5 plus 1 is going to be 6. 5 minus 3 is 2. So f of 5 is going to be negative 1. So we have this point 5, negative 1. And that shows us where the function is going to be. It's going to be close to the asymptote over here and close to the asymptote over here, all in this fourth quadrant. Let's take a look at another one where things are going to be a little bit different as far as the asymptotes, but it's going to follow the same pattern. First things we want to do are factor. In both the numerator and denominator, we have a common factor, so we can factor out an x, so we're left with x squared plus x minus 6. And in our denominator, we could actually factor out a 4x squared, and we are left, just kidding, a 4x, and we are left with x minus 3. We notice that we can factor out nx. It doesn't matter that it's being multiplied by the 4, since it's all multiplication. There's no addition or subtraction. So we're going to have a removable discontinuity at x equals 0. So in order to figure out what that y-coordinate is, so we can graph the open circle for the whole, we're going to find f of 0. So we have 0 squared plus 0 minus 6 divided by 4 times 0 minus 3. So that is going to be negative 6 divided by negative 12. So our removable discontinuity is at 0, 1/2. So we go to 0, 1/2 on the graph and put an open circle. But since there's a removable discontinuity at x equals 0, we know that the function is not going to have a y-intercept. Let's factor the rest of this. This numerator is going to factor to x plus 3 times x minus 2. There's nothing else that we can factor out, so there is only one removable discontinuity. Not every function is going to have a removable discontinuity, and some could have more than one. So for our vertical asymptote, we are going to set our denominator equal to 0, so we are going to have one at x equals 3. So we go ahead and draw that dotted line to represent the asymptote on the graph. This function, because it has an x squared in the numerator and an x to the first in the denominator, is going to have an oblique asymptote. So how we find the oblique asymptote is by doing long division. So let's long divide this x squared plus x minus 6 by 4 times the quantity x minus 3. Now, one thing that I like to do to make this a little clearer for myself is to do division in 2 steps, so that we're not working with fractions in our long division. We can divide by the x minus 3 and then When we're done that, we will divide by 4. So all of our fractions come at the end. So we do x squared divided by x. We end up with x. Multiply that by our entire divisor. Subtract this step. So we end up with 4x minus 6. 4x divided by x is 4. And stop there. It does not matter the remainder because the asymptote is only going to model the end behavior of this rational function. It is not going to affect anything towards the middle of the graph. And as x approaches infinity or negative infinity, this remainder is not going to be relevant. So just do your long division and you can stop once you get a quotient. But we still need to divide that x plus 4 by that 4. So we end up with our oblique asymptote is 1/4 x, because just taking that 1x divided by 4, and then plus 4/4, which is 1. If we do not have a y-intercept that is an integer, then what I would recommend is finding an x value that you can substitute into that oblique asymptote that will give you an integer value so that then you can use the slope to find the other points. So our y-intercept in this case is 1, and our slope is 1/4, so we can go up 1 over 4 or down 1 to the left 4. And we draw our asymptote. There we go. Then let's look for some zeros. Let's set our numerator equal to 0. So our zeros are going to be at -3, 0 from this x plus 3 term. And then our other 0 is going to be at 2, 0. So we have -3, 0 and 2, 0. So this section, the function is going to be close to the asymptote, have this 0, have what would be that y-intercept, but is a removable discontinuity. Come back. That's not my greatest curve, but that's better. And then close to the asymptote. Then we need to figure out what's going on over here. So let's just pick a point that we could substitute into the function, like 4. So f4, remember we're substituting it in over here because that is what the function is going to look like everywhere except x equals 0. So we have 4 plus 3 multiplied by 4 minus 2 divided by 4 times 4 minus 3. So we have 7 times 2 divided by 4 times 1. You can factor out a 2. So 7 halves. So about, well, exactly 3.5, which would be about here. So the function is going to be close to the asymptote, intersect this point, and go close to the asymptote. We want at least one point that we have the exact value of on each interval of the graph. Now, let's take a look at one more here. So here, let's factor. And then our denominator, we can factor out a 4x. And in this case, we are going to have more than one vertical asymptote. So we have no removable discontinuities. Our vertical asymptotes we will have at x equals 0 and x equals 3 because we set each of these terms in the denominator equal to 0. So don't get thrown off with that 4. A mistake I see sometimes is people saying that's 4 or -4. But remember, you have to divide both sides by 4, and you're still going to be left with x equals 0. So we'll draw our asymptotes here. Then we want to compare our greatest exponents. So in the numerator, our exponent is 2, our denominator exponent is 2, so it is going to be a horizontal asymptote at a ratio of the coefficients. So it's going to be at y equals 1/4. Now we need to find zeros and the y-intercept. Well, there's not going to be a y-intercept because of that vertical asymptote, that essential discontinuity, because if we substituted 0 into the function, we'd end up dividing by 0 and not going to work out, so there's no y-intercept. For the zeros, we set our numerator equal to 0, so we have -4, 0, and 1, 0. Let's go through and factor those. So this interval, we know what's going on with the function. It's going to be close to the asymptote, hit the intercept, and then come close to the asymptote again. Over on this right side, it's just like the other ones we've done. We need to pick a value and substitute it in. So let's say, 4. So we've got 4 plus 4 times 4 minus 1 divided by 4 times 4, and then 4 minus 3. So we have 8 times 3 divided by 16, factor out an 8, so 3/2. That is a common number in these today. So it's going to come close to the asymptote, intercept this point, and then go close to the asymptote. Now, what's going on in between the asymptotes, things can get a little different. Sometimes it's going to look like a parabola. Other times it is going to behave more like a cubic function. So we have to substitute 2 points in to see what's going on. I understand that we've got an asymptote here, that horizontal asymptote of y equals 1/4, but that is only modeling the end behavior as x approaches infinity and negative infinity. So when we have multiple vertical asymptotes, things can get a little different around that asymptote, so we can cross the asymptote. So what I would like to do here is just substitute 2 more points in. So we'll do 1/2 and then 2 in order to see what the y coordinates are going to be. Let's do f of 2 first. So we've got 2 plus 4 multiplied by 2 minus 1 divided by 4 times 2 and then 2 minus 3. So our numerator is going to be 6 times -1. Our denominator is going to be 8 times -1. Divide out the -1s, divide out a 2. So it's going to be 3/4, which is greater than this asymptote. So we know that the function is then going to go, as x approaches 3 from the left, the function's going to approach infinity. Now for 1/2, it's less important that we get the exact value. We really just want to see, is this going to be positive or negative, so that we're not spending all day adding the fractions and then multiplying and doing things there, even though that is something that we are entirely capable of doing. So 1/2 plus 4, substituting it in here, 1/2 plus 4 is going to be positive. 1/2 minus 1, that next part of the numerator, is going to be negative. So multiplying a positive and a negative, our numerator is going to be negative. Then our denominator, 4 times 1/2, is going to be positive, and then 1/2 minus 3 is going to be negative. So our denominator is also going to be negative. A negative divided by a negative is a positive. So our function is going to look, between the asymptotes, a little bit like a parabola. Thank you for watching, and let me know if you have any questions.